going to start with a bit of geometric motivation, which I guess we're going to get to combinatorics later. I really do more commutative algebra, so it's going to be fun. There might be things about the combinatorics of this that you will be able to tell me that I don't already know. So we're going to start with two smooth projective normal toric varieties. And an embedding of y in x. So we want y to be a toric subvariety of x. And I'm going to write mx and my for the character lattices. Okay, so if you don't know what these things are, probably you'll be able to black box this in a second. We're going to eventually get a lattice. So, but if we do know what they are, if you have a toric embedding, then you also get a map of character lattices in the opposite direction. And so I'm going to draw a big commutative diagram of all of these. So the character lattice of x fits into a short exact sequence with the Picard group of x, or I guess the class group and the Picard group are the same thing because we've assumed that x is smooth. And similarly, for y. Okay, and if we have a map from y to x, then we get a map from like this. And because it's an embedding, we're going to have that it's surjective. And so I'm going to take a lattice that comes from the kernel of this, which I haven't left myself space for. But I'm going to take the kernel of this map of character lattices. And this is the lattice that we're going to care about. So if you don't know what this means, then you can think of us just having a lattice, and we're actually going to think about it as being in z to the n. So this is an injection, and this is an injection. So there's maps like this, too. We're going to think about a lattice in Zn, and the sort of geometric motivation for from like algebraic geometry is that it's coming from some map of character lattices from a toric embedding. Okay, so we're going to have a couple of different rings floating around, so I think I'm going to try to actually leave them up somewhere. So the first ring is going to be just the polynomial ring in n variables, where this n is coming from here. So this is going to be the number of rays in the fan for x. Or it's going to be like the place where our lattice lives. So this polynomial ring is the total coordinate ring of x. If you want to think about it that way. It's going to be a polynomial ring in n variables. Okay, and we're going to define a lattice ideal. So the lattice ideal of L inside z to the n is defined to be the ideal generated by binomials. It's going to be a binomial ideal. And the generators look like x to the a minus x to the b. So here I'm going to use x to the a to mean the product. Let me just write it like this. So we've got n x's, right? So I want to raise the first one to the, if I can actually write this. We're going to raise the first one to the a1 power and up to this. So a here is a vector in z to the n. Well, actually, we're going to see in a second, like this, the generators are going to look like x to the a minus x to the b, where these are two monomials, and then we want a minus b to be an L, but we want this ideal to be inside S. So here, a and b have to actually be natural numbers, but a minus b can have integer entries that are negative. So this is going to get a little confusing. There's going to be other rings where we do have negative exponents. So these exponents are positive, but their difference might be negative. So we're starting with a lattice that includes negative entries, and we're kind of splitting it up into the positive and negative parts a little bit. We'll see an example of how to calculate these generators. but we're finding all non-negative things so that when you subtract them, they end up in this lattice. Questions about this definition? Okay. So one reason you might care about this from the geometric motivation is that I is the ideal of y in x, the way I've set it up. So I said this is like the total coordinate ring of x, and if you want to know what ideal defines your subvariety y, this is the ideal. Why is that the case? Basically, this y, so a toric variety is like the closure of a torus. We've heard this a couple of times already. So the image of y and x is sort of going to be the closure of the image of a torus over here. And if you think about the map of tori, then you can see that these generators are satisfied. Like if you think about what it means to be an L, well, one of the torus has coordinate ring the affine semigroup ring of this, and one has coordinate ring the affine semigroup ring of this. And so if you have 2 points in your torus and the difference, like, how do I say this? If you think of actually plugging a point of your torus into here, having a minus b and L is exactly going to tell you that they go to the same place when you go down here. So it's a little bit of a pain to disentangle the definitions, but this is actually the ideal defining y and x, and that is maybe one reason why you care about it. And it sort of comes from the fact that this is, I mean, some people call these toric ideals. They are like the ideals that define tori and other tori. And so then when you take the closure, kind of nothing happens. Okay. So we're going to try to resolve, well, I said we're going to resolve normalizations of toric ideals. We're going to start with the not normalization case. And I need to tell you what I mean by resolve. So in case, probably this is very familiar to some people and maybe not to others. So a free resolution of an S module M is an exact complex of the following form. So we're going to have, I'm going to write them, I'm used to writing them right to left because of Macaulay too. So we have M. Then we're going to have, I guess I should probably give myself more space. Okay. The free here means that we're going to resolve this in terms of free modules. So we're going to have some free module, which is going to look like S to some power. These powers are usually called beta. We're not really going to need that notation. And then we're just going to keep going. So, and it's a theorem that it'll end. Because this is a polynomial ring, Hilbert's G theorem says that it'll end after n steps. So if you're not used to thinking about this, it's kind of like giving generators and relations for a group or something else. Like this is a free module, so you can, it's going to map onto some generators of M, and then this free module is asking what relations do those generators have, and then, but then it turns out you can just keep going. You can have relations amongst the relations, and so on and so forth. And so this gives some information. I mean, it gives combinatorial information in terms of these numbers about the ideal you started with or the module you started with. We're going to be doing this for an ideal. And there's a whole bunch of theorems about like what do we know geometrically about our variety based on like these numbers, based on the degrees that appear. I'm not dealing with the grading. If you want to have this be homogeneous, you can like twist these S's, and everything I say is going to work for the graded setting too. If you have questions about what happens with the grading, I can answer them, but it's a little bit confusing, and so I'm just going to not deal with the grading. But everything here can be made graded, and so which degrees show up gives information about the original ideal. So these are like invariants that commutative algebraists care about. And so our first goal is going to be to find a free resolution of S mod I. So I'm going to fix this L the whole time. So we have some L, we're getting this I, and then we're going to try to resolve S mod I. And I'm going to be basically explaining a lot of things that Dave Bayer has done. And then I'm going to explain like a more general situation where we're able to get the normalization as well. But that situation is more confusing. So I'm going to start with the one where we're just doing S mod I. Questions so far? OK, so there's kind of a trick to this. We're actually going to resolve something else first. Before we do this, we're going to use a resolution of another module to get a resolution of this. So we're going to need another ring. T is going to be the same variables, except we are going to invert all of the variables. So this is some Laurent monomials. And we're going to define a module over this ring, resolve it, and then use that to get a resolution of S mod I. OK, so the monomial module of L is defined to be the module. And I'm just going to use M for it. Before, this was a generic module. Like you can do this for any module, but I'm going to just fix M to be this module, just like I'm fixing I. So we're going to take the S module generated by things of the form x to the c, where c is an L. OK, so in this ring, and this is inside of T. So we're allowed to have negative exponents now because I've just added the negative exponents to T. And so this is maybe like a simpler version of this. OK, we want our exponents to be an L. Here we needed our exponents to be positive or non-negative, so we somehow wanted their difference to be an L. And here we're just going to take the things in L, and we're going to take their exponents in T. But we're going to take the S module generated by these, not the T module. And so this is infinitely generated as an S module in general, because we could have like infinitely negative x to the c that appear, and we're only allowed to multiply them by non-negative elements of S. OK, so this is infinitely generated. As an S module. OK, so the way that we're going to get around this and make this finitely generated is by looking at the group algebra, which I'm also going to put over here. So S adjoin L, this is maybe familiar notation that we're going to take the semigroup here and take the semigroup ring over S. But S already has some variables too, right? So we're taking, this is going to be S adjoin y to the c for C in L, which we're thinking of as living inside T. And then if you remember, this is already right here. Like this already has variables in it. So we've got the x's still, and now we're adding some y's. These y's might have negative exponents, but we're not adding all of them. We're only adding the ones that are inside L. OK. So there's a couple of steps that we're going to need here in order to get a resolution of S mod I. So the first step is that S is an SL module. But we're not going to take S to be an SL module in the obvious way. Like it looks like, OK, yes, we just mod by L. Or we have S, like, yeah, we have L act by 0 on S. We're actually not going to have L act by 0. We're going to have L act by 1. So we're not going to take SL mod L. We're going to take SL mod all the things of the form y to the c minus 1. So this is part of, I said that you can make all these things graded that I'm going to say. This is part of why the grading gets annoying, is because this thing doesn't look homogeneous, right? So you need to be careful about what group you're grading in. And you can make it work. Like you've got to take some grading and quotient by L, basically. But it's a little bit of a pain. OK, So, but with this, S is an SL module, right? Like this is a quotient. This is isomorphic to S. All the y's act by 1. Okay. The second step is that M is finitely generated over SL. So it's not finitely generated over S, right? But it is finitely generated over SL because you've just added the things that were making it not finitely generated, right? Yeah.
You're adding one variable to each C? That's the notation there?
Oh,
Or is it just one variable?
oh, sorry, did I write it wrong? One sec. Wait. Oh, for this? I think it's just not supposed to be inside T. Wait, M is supposed to be inside T. This is, where'd it go? I think I just wrote the wrong thing. Yeah, sorry, I just wrote the wrong thing here. This might help. So this is inside S where we've now added, yeah, that's important. So we started with just the x's, then we added the inverses of the x's. Now we're adding inverses of y's too, but we are just including the elements with exponents inside. Thank you, inside L. So we're not adding a new variable for each C, really. We're like, it's inside here. Yeah. Other questions? Okay, so M is not finitely generated over S, but it is finitely generated over S adjoin L for pretty obvious reasons, right? None of these things are particularly deep, but it is surprising that we're doing this at all. Like, why are we doing this? And so something fun is going to happen at the end. So the way that you get this to happen, and Jonathan pointed out that we need to be careful about the x's and the y's. So M is a finitely generated SL module where we just send the y's to the x's. So there's a map from SL to T. Oh, it doesn't go up. Okay, where we just send y to the C to x to the C. And M lives inside here. So this way, I mean, it's actually a cyclic SL module, right? It's very finitely generated because we've actually just put all the generators are in the image of this, right? Questions so far? Okay, so then the reason why we did this is because if you tensor M over SL with S, so here S is an SL module like this, and M is an SL module like this. We're going to tensor them together. This is actually just S mod I. So if we want to resolve S mod I, well, we're going to resolve this first, and then tensor to get a resolution of S mod I. And a paper by Bayer and Sturmfels from 1998 says that, and I'm going to put cellular here. We're going to see what a cellular resolution is in a little bit. So that if you start with a cellular resolution, of M over SL, and you tensor with S over SL, then you can get a cellular resolution of S mod I. Okay, so they show that there is an equivalence of categories here. It's a little bit subtle because you need to be careful. This tensor product is taking you between two different categories, right? This is not like a tensor product within one category. So if you think of this as a tensor product in one category, then it's not flat. Like, it's not obvious that resolutions should go to resolutions. But when you go between the two different categories, then you actually resolutions of M. Like we're using what M is here, I guess, to do this. It's not true that this functor, like in all cases, takes resolutions to resolutions. So this is somewhat subtle, but it's going to help us achieve our goal, which is to resolve this. Questions about this? OK, so now I'm going to say what the new part that me and my co-authors were able to show is. And I'm mostly going to explain the difference in the setup via example, because the notation gets rather cumbersome. So actually, let me just edit here. This is joint with Christine Burkesh, Greg Smith, and Jay Yang. Gotta get the alphabetization right. OK, so I'm going to say a similar construction is possible. We're going to do an example. For cellular resolutions, on a stratification, of RL. OK, so I haven't told you what a cellular resolution is yet, and I'm going to. But so far, we are trying to start with a resolution of M over SL. And the generators of M are like the lattice points in L, right? Like L is a lattice. The generators of M are coming from the exponents of the points of L. What we're going to do is we're going to actually allow some additional points to occur. So we're going to look, instead of at L, we're going to look at the real span of L, which is some real vector space. And we're going to get a more complicated cell structure where there are some additional generators of M besides just the exponents in L. So before we had M, need some more chalk, M generated by x to the c for C and L. And now we're going to have M generated by the labels of some points in RL. And I will explain how this works. But first I want to say a corollary, which is kind of why we were interested, or not the only reason why we were interested in this. I'll talk more about its connections with other things at the end. But one important consequence of this, which was in the title, is that for a particular stratification, which I'm going to use as the example, so for the ceiling stratification, what we're going to get when we take our new M and we tensor with, well, we're going to do the same thing. We're going to tensor over S adjoin L with S. We're actually going to get the normalization of S mod I. So this is the normalization or the integral closure. You could also, I think, I'm not like 100% sure of this, but I think that you can, if you're not used to thinking about normalization of rings, you can think of S mod I is going to be, I believe, the semigroup algebra. Oh, it's like this. And then you want to think of taking this semigroup and normalizing the semigroup. So if that makes you happier, or the saturation. Okay, so we can actually resolve something new using this machinery. This is not the only new thing that we're able to resolve, but this is one of the ones we were most interested in, is being able to resolve the normalization. I'll say a little bit at the end about why we wanted to resolve the normalization.
So, you wrote that isomorphism over there, and now is it the same as normalization, or?
Sorry, so this is a new M. Maybe the M is, maybe let me just give it a different notation. So we can call it M prime, where my M prime, this will help, like this. Yeah. So we're doing something different. If in some cases they will be the same, like if your semigroup is already saturated, then you're just going to get this back. But in general, it's different. Yeah. Do you have a question? No.
I think I'm a little bit confused.
Yeah.
Do you have any assumptions on L that I don't see, or is it just an arbitrary subset of Z to the N?
So it's a subset of Z to the N coming from the description that I gave at the beginning, like coming from a normal toric embedding. I think that means, what does that mean? I think that means that it's torsion-free. Something a lattice. Does it mean anything else? You can classify which L comes that way.
Are you guaranteed that L is a subset? I mean,
no,
okay,
no. So this, yeah. This notation is like misleading somehow, where you're taking relations in L that actually occur in N to the N. So like L is not inside N to the N. So this is sort of similar to what we were doing when we defined I, where like two things are equal in N to the N if they differ by something in L. Like, sorry, two things are the same in here if they differ by something in L. But it's not the case that the elements of L are actually in here. So yeah, that's a good question. Other questions? Okay, so let me give you an example, which I hope you'll sort of be able to see how we could generalize this. So we're going to do, so to explain what I mean by this, which is very vague right now, we're going to get a cellular resolution of some stratification. I'm going to actually do one, and hopefully you can see what the general situation might be. Okay. So we're going to take y to be a point, the torus fixed point inside x, which is going to be the Hertzsprung surface 2. Okay, so point you're probably OK with. Hertzsprung surface 2 is a particular example of a P1 bundle over P1. The 2 just means that there's a whole family of them that are indexed by the natural numbers. So there's Hertzsprung surface 0 is P1 cross P1. Hertzsprung surface 1 is a different P1 bundle over P1, and so on. OK, this is a toric variety. So if you like getting them from fans, it looks like this, where this is 2. So like it's -1, 2. And we have all these cones. It's supposed to be projective. It is smooth. It's coming from a fan, so it's normal. And this is going to be the torus fixed point inside here. OK. So our diagram from the beginning is going to simplify a little bit because we're just using a point. So the characters of this thing are 0, and its Picard group is 0. And so if you remember at the beginning, we had 3 rows. We started with the presentation of the class group of X, which here X has dimension 2. So MX has dimension 2. So we had MX, and we had the number of rays, which is 4. So this is 4 rays. And then we have the class group, which we're not actually really going to care about here. It just finishes out this exact sequence. So this is the characters, which are 2-dimensional because X is 2-dimensional. And then the point is stupid. These things are all 0. So this is going to simplify our situation a little bit and make it easier to draw. So what is the kernel of the map from Z2 to 0? Well, it's just another Z2, and that's going to be our L. So this is an isomorphism. And then we're going to be interested in the embedding of L in Z4. And so we're going to care what this map is here. And that map is given by the rays of our fan. So if you know how to get the presentation of the Picard group, this map here is given by the rays in the fan. So let me maybe write in a different color. So this map here is going to be given by the matrix, where we put the rays of this fan into a matrix. So 1, 0, 0, 1, negative 1, 2, and 0, negative 1 is going to be this map here. So that's how, so our L is just going to be Z2, and it's embedded into Z4 by this matrix. Questions about the setup? OK, so I said we're going to get a stratification on RL. So RL is just R2, right? So, oh, actually, first I want to say what I is. So here, S, well, maybe I can just write it over here. We got S. I'm going to diverge. Yeah, so maybe let's get rid of these ones and do new ones, because I'm going to diverge from the numbering scheme that I had here, because Macaulay 2 starts at 0, and I did not want to try to shift these from my normal, like in my head, the Hertzberg surface is always numbered like this. So, OK, so we had S is now, I'm going to start at 0. Like this. So T is like this. And then we'll start with that. So what is I? Well, I guess I'll write it over here too. We're supposed to take x to the a, which in this case is going to be a whole tuple, minus x to the b, where their difference is in L. So let's look at the generators of L and think about how you can have your difference in the span of these two things. So we have 4 variables, right? So we're looking for 4 exponents and 4 exponents so that their difference is in here. There's an obvious way to get some, which is to take the positive and negative parts of this. So like if I claim that x0 minus x2 is in here, because this has exponent vector 1, 0, 0, 0. This one has 0, 0, 1, 0. If you subtract them, you get this. Yeah? So separating the positive and negative parts of these is one way to get generators, and I'm just going to claim that this is all the generators here. There's Grosvenor basis ways to do this. There's other ways to show that you've got them all. I'm not going to worry about that right now. So certainly these 2 generators are in here. This one I got the same way. If you take the exponent vector 0, 1, 2, 0, and you subtract the exponent vector 0, 0, 0, 1, you get this. And it turns out this is all of them.
Is that because it's principal for the second column, and then the first column is just adding a variable without touching it?
Yes, I think so, but I would probably need to think harder. Like somehow you need to know that you can't, I think you need to know that you can't get any other like support of positive and negatives by taking combinations, and I think that I don't know, we can discuss it after if you want.
Your first column is just tacking on a variable.
Yeah, I think the fact that
the second column, it would obviously be all the generators, so.
I think that's right, but I would need to think a little bit harder to be positive. Other questions? OK, so that's our I. So we're going to be trying to resolve the normalization. I didn't actually write down what the normalization is, unfortunately. You do have to add something. Maybe somebody can figure out what it is. Oh, and I guess I should say we're normalizing S mod I. So, but I said we're supposed to get a stratification on RL, right? And I didn't explain what that is. So let's do that. Here, RL, well, L is just Z2, so this is R2, and I said I was going to do the example that comes from the corollary. So part of what we do is we like define stratification and say what is the full generality where you can get this construction to work. But I'm just going to give you one example of a stratification, and hopefully you can kind of see the type of thing that we would want. So I'm going to have the stratification come from the ceiling function on R4, where this R4 is coming from this Z4. So L is inside here, right? And we're going to take ceilings in here. OK, so let's actually do this. So let's start with the I'm also going to show you what a cellular resolution is, hopefully. So what we're going to do is we're going to get a cell complex. Or maybe we're going to get a cell complex inside R2, whose vertices include the lattice points of L, but there's going to be additional vertices. OK, so how am I going to define this cell complex? Well, I said I'm going to take ceilings, but it's going to be a little bit confusing to look at because we're going to draw a picture in R2, but we're going to be taking ceilings in R4. So let's start with the lattice points of L. Oh, and I should say, too, we're going to label all the cells with monomials. Just like how we got the generators of M. Remember the generators of M were x to the c. These are going to be like our new generators, so they're going to be monomial labels. OK, so let's start with L. Certainly, we've got the point 0 in L. That thing is going to have label 1, because x to the 0 is 1. OK, now I'm going to draw L in like the plane, except this is going to be the x direction. This is going to be the y direction. So it's spanned by two things. And if we go in the x direction, we're going to use this one. And the y direction, we're going to use this one. OK, so if we go one lattice point to the right, what are we going to label that? Well, we're supposed to take the x's to this exponent of this element in L. So this one, this is going to be a Laurent monomial because that was OK. And this is going to be x0 over x2. Question about how I got that? OK, so similarly, if we go up, we're going to use the other vector, and we're going to get x1 x2 squared over x3. OK, so I told you that we're supposed to be taking ceilings, but these are all integers. So we haven't had to take any ceilings yet. So these labels are all going to be the same as if we're just doing the original M. We don't have any stratification. These are the labels that we would have done if we were just trying to compute the resolution of S mod I. But now we're going to get some additional ones. Let me do this one too, maybe. So this one is going to be the product of these two, right? x0, x1, x2 squared over x2, x3. OK, so in between these points, we're going to take ceilings. So let's think about going along this line here. As we go this direction, we're supposed to be like gaining an x and losing an x, gaining an x0 and losing an x2. So if you're in between, you would think that you have like half an x0 on the top and half an x2 on the bottom. And we're going to take ceilings. So the one on the top is going to become 1, and the one on the bottom is going to go away. Because we're going to have like x0 to the 1/2 is like sort of what we're thinking of. We're going to have x0 to the 1/2 and x2 to the minus 1/2, and we're going to take the ceiling of that. Does that make sense? And we're going to get this. OK, so that's fine. The same thing happens over here. I'm not going to label all of them. Let's think about going up. So if we go up, we're supposed to be getting x1s and x2s and losing x3s. Just like here, the x3, when we take the ceiling, it's going to go away. As soon as we leave 1, we're going to end up with part of an x1 and part of an x2. So we're going to have an x1, x2. on the top and nothing on the bottom. But if you think about going this way, we're going to hit an integer faster than this way. Like this way, this whole time we're going to have a fractional x0 and a fractional x2. But if you go up, there's going to be a point where you are supposed to have exactly one x2, right? So we're going to actually get a new vertex here where we hit another integer. Okay? It's still going to be labeled x1, x2, so that's not that interesting. But when we pass it, then we're going to have an x1, x2 squared. So the reason why this is a vertex is because there's actually a line that goes like this where you hit the integers. So this picture is actually going to look like this. So let me explain where these lines are coming from. Like as we went up here, we hit some point where we got exactly an integer number of x2s. If you think about this is embedded via this, and so if you think about when you're going to get exactly one x2, it's going to be like when you're normal to this somehow. So like over here, we had part of an x0 and part of an x2, and so when you go up, you hit an integer number of x2s faster. So if you work it out, this is like where the ceiling actually, where your x2 exponent is actually an integer. And so we could label out this whole picture, and it keeps going, right? Forever, in all directions. Does it make sense how I got this?
Why is this an interesting construction? Sorry.
Very valid question. So,
It's a normalization.
yeah, one commutative algebra answer is it makes the normalization. We're going to get a resolution of the normalization. This came from symplectic geometry, actually. So another answer is it appeared somewhere else, and we were like, what happens if we try to use it too? And then maybe a third answer is that we are actually trying to replicate a construction. Like, we're going to get a resolution that agrees with a construction that actually did come from the symplectic geometry version of this, and so we're actually able to connect the two, sort of. But also, in a way, we don't really know why these pictures are. It seems like the mirror symmetrists have some belief of why they think these pictures are nice, and I don't know what it is. Like, it solves, maybe let me say more about this at the end, which isn't going to be that long from now.
But even the Taylor resolution for monomial ideals is based on taking least common multiples.
Yes.
And our monomial, even in the monomial case, our cellular resolutions are based on taking least common multiples.
Yeah, so
Note
this is...
that her construction here is effectively putting the least common multiple on each edge. She didn't say that. But,
yes,
and adding
true.
points, which is mind-blowing.
So somehow, another way of thinking about this is like, if you try to do the stupid thing, and you're like, okay, well, you know what these labels you want to be, and then you like try to make a cellular complex, and then you're like, okay, what do I want the labels in the middle to be? You're going to have these lines that cross, and then you're like, okay, well, it's kind of if you try to do the stupid thing, then you run into a problem, and this is like the stupidest possible solution to your problem, and it doesn't seem like it would, but it's legitimately surprising that this gives anything interesting. Yeah. Okay, so let me actually go to the end of this. So, all right, what have we done? We've gotten our stratification on R2, and we're supposed to use this to make a module, resolve it over SL, and then tensor with S. Yeah? So our module M prime is going to be generated by the labels in this picture. If we had a more general stratification, our stratification is going to give us some labeling and some cells, and we're just going to take the module generated by the labels. As Davis pointed out, it's enough to take the vertices. Everything else is going to be an LCM. But that's like pretty obvious, but also confusing. So we're going to generate by the labels, and now we're supposed to resolve. So we want to resolve M prime over SL. And this is where the cellular part of the cellular resolutions are going to come in. This picture is actually going to tell us how to resolve M prime over SL. So what we're going to do is take one summand of SL for each type of cell up to translation by L. Okay, so this is kind of why this whole machinery is useful, is that you can read off the resolution of M prime from the picture. It's not obvious that this is going to work, but it's part of the theorem that this works. Okay, so how many points do we have? Well, we've got infinitely many, right? But up to translation by L, there's only two types. There's this type. Is anyone colorblind? Okay. We got that type and we got this type, right? All the other ones are translations by L by these big lattice points of one of these two. So we're going to have two, maybe let me write them. We're going to have two copies of SL here.
Sorry, actually, what do you mean by types again?
Yeah, so I'm saying that up to translation by L, like if you're allowed to translate by L, you can get from any lattice, any vertex in this picture, which goes on forever, to either here or here. So L was like this, and this. So if I'm on any of the like real vertices, then I can translate by L back to the blue one. If I'm at any of these like half integral ones, then I can translate back to a red one.
L has two orbits.
Yes. Cool. All right, and then we're going to get 5 types of lines. So there's 1, 2, 3, 4, 5, and then all the rest are translates of those. And then we're going to get 3 types of like cells. That's easier to see, 1, 2, 3, and all the rest are translates of those. That's a 5. Okay, and then we're going to tensor over SL with S. So, okay, what does that do? It's just going to make all of the SLs into S's. And then the theorem is that this actually resolves a normalization. And I want to tell you how to get one map in here. So I said we're doing a cellular resolution. We have a cell complex. We're taking a cellular resolution. Maybe people have heard of that concept before. It's a way of taking a cell complex, a labeled cell complex, and getting a resolution. The way we're going to get the maps is by dividing the labels. And I want to show you one of them because you actually can end up with binomial maps in this. So we get the maps by dividing the labels, which will always give you a monomial. Even though those things are Laurent monomials, the way we've set them up, all the divisions will give you honest monomials. So let's do one example. So on the bottom, we've got a line like this that goes between 1 and x0 over x2, yeah? And I said that the label in the middle is x0. Okay, so if we divide these labels, x0 over 1 gives you x0, x0 over this gives you x2. So our map to these, our map in this is somehow going to take the SL corresponding to this type of edge into the SL corresponding to these points, but these points are the same point. Like they're both blue, right? So actually, once we do this whole thing, they're going to go to the same place, and so we're actually going to get an entry. So we're actually going to get an entry in our matrix that looks like x2 minus x0. That goes between the copy of S that corresponds to this side to the copy of S that corresponds to these two blue points in here. And then you can get all of them like that. And so you get a resolution of the normalization. And so I want to say a tiny bit more about how this connects to other things. So one of our motivations for this was to sort of give a straight commutative algebra interpretation of a resolution of the diagonal by Hanlon, Hicks, and Lazarev. that uses these pictures. So they actually cared about symplectic geometry and actually used these pictures. And so we're able to show, not only do we get a resolution of the normalization, but we actually get the same one as they do. And they were motivated by something totally different. So it's cool to be able to give an explanation. It's like purely combinatorial algebraic machinery to get the same thing without having to think about symplectic geometry or anything. And in that sense, it's kind of a generalization of a different paper by Bayer, Popescu, and Sturmfels from 2001. It was not immediately obvious how those things are connected. So that was one of our motivations, was to explain, like this normalization showed up somewhere else, and we were trying to like explain where did that possibly come from? Can we actually give an algebraic explanation of why we get the normalization out? And if you dig through the proof of this, you can kind of see why adding these points is like the right thing to normalize. So I will stop there.